Here we would like to show you one of the key features of the software, the weld recognition module. The power of the weld recognition module will be shown by combining it with the predefined grain standard, the DIN 50018. In the example, the required fatigue resistance of the complete model will be checked and differences between weld and plate material will be shown. To start this lesson, I already opened the VMAP file. As you can see here, this is a piece of a crane boom with different loadings to it, and we would like to do a fatigue check and check both plate materials and the welds. When we start SDC Verifier, we start with a new project. We use the active model from VNAP. We type in a number for the project details. Example 2014-001, for example, and example weld recognition. Calculation. Then we select who is doing the calculation, and for who. In our case, for the example customer. And then we can choose between working in a separate window or choose to use SDC Verifier completely embedded into VMAP. As you can see, SDC Verifier is opened in a separate menu bar next VMAP environment, and we can immediately start by recognizing the welds of this model. Therefore, we click on weld recognition. In this weld recognition window, you will see some options how to recognize welds for the same properties in a weld or two different properties. By clicking on find welds, we will find all welds. After recognition of all welds, we can select a couple of the welds and show them, for example, with a number. As you can see here. Or we can select, for example, all of them and show them with a color. Okay, looking at these results, it seems that all welds are selected. So what we are going to do is we're going to update the element direction. That means that the element X direction is along the weld and the element Y direction is perpendicular to the weld. For the exporting options, we can set the welds to be exported in a VMAP group. That's this button. We also want to have it in a component group in SDC Verifier itself, and we don't want to have only all welds in one group. We also want to make it an extra group for intersection welds. We always have a stress perpendicular to a weld because it's either perpendicular to one weld or perpendicular to the other one. Okay, Now we're done with weld checking. For example, we can now start directly by making a model setup report. Therefore, we start the wizard with the pre-prepared model setup. You can see here. Okay, as you can see, since we filled in all our data already, that data comes back in our report. The only thing we want to change is that we want to have a plot from our model in the front page. The model setup settings already filled in by selecting the standard model setup report, and we go immediately to the report designer. We save the report wizard. In the report designer, you can see on the left window everything which is included in the report, and on the right we can see everything which can be added to the report. We can, for example, select one section and generate only that part. In this case we can see a plot of all welds, or we can, for example, show all components. And since we created, the only components we have is created by our weld recognition tool, you can directly see here all intersecting welds, and on the next page we will see all the welds, whether they're intersecting or not. If you want to generate the full report, you have to click here, and for making a Word report or exporting it to a PDF version, you have to click here. We first generate a complete report. It takes a while, but you can at least see directly how much time it takes. And we can directly view how our model looks. We can see different properties, different sections in our beam, top and bottom plates, stiffeners, side plates, and the description of all the stiffeners, size, shape, moments of inertia, area, everything you need from a beam result, and what we already saw, the components generated. And also the description of each individual load. You can see here load number 1 is on the outmost point of the boom. Load number 2 is slightly more inward. Load number 3 is halfway between load case 2 and 4. And constraints is everything is constrained at the back here, and supported here in the middle, in this middle beam. So it is a quite simple design, which is ideal for testing our weld recognition model for fatigue. We are going to export this to Word. The Word file can be downloaded from our website, and also the PDF version of that. In the Word report, you can directly see that the same setup of your report is in the navigation pane. So first page is what we expected. We can go easily also swap to the different positions in our model description report. Here is the stiffener description, the sizes, shapes including a picture, and stress recovery points, and where are they located. Components already discussed. Here are all intersecting welds, and all welds found in the construction is plotted here. Yeah. So with SDC Verifier you can make a complete description of your report with 2 mouse clicks. Let's go back to our model. We want to save the report. We did all the model preparation, we recognized all welds, and now we can generate the load cases to calculate. We already looked at all loads and all constraints, and now we need to combine them to make new individual loads. Here are the FEM loads. We already saw the description. We have 4 load positions and we have the standard gravity, and we only have 1 type of constraint. By selecting all the FEM loads and all the constraints, all possible combinations are automatically made. So here you can see gravity and the 4 load positions. For load sets we need to combine all these forces, and for the example we keep everything quite simple. We don't do complicated partial safety factors, we use all combination factors 1. So what do? We always have gravity, of course, and then for each of the load sets we have 1 of the individual loads active. So now we're done. We have here our 4 load cases, and we need, for the fatigue calculation, we need to define all possible load situations. Remember that for fatigue calculation it is not only important to find the maximum results, but we focus on the stress difference, and for the stress difference you also should watch for the minimum load set. So the base load case, only gravity, which is an individual load, should be included in our load group as well. So we write all fatigue calculations and a complete list of load sets and the base load case, only gravity. We can now calculate. By clicking on this button we directly control everything in VMAP, and we can wait for the calculation. In the meantime I will try to explain you a bit more about fatigue calculation and the implementation in VMAP. The implementation according to the crane code depends basically on 2 things. We have a fatigue resistance, which is defined by notch group and the number of required load cycles, and we have some material limits which depend completely on the type of material used. If you want to know more on the theory of fatigue calculation and how is it implemented in crane codes as this DIN 50018, I refer to our website, and we made a PDF with a short description of fatigue calculation. For the fatigue resistance factor, we need to select the number of load sets, and we want to select the load spectrum of our load cycles. In our case, we select a moderate load spectrum, which means, according to the standard, that the structure is repeatedly loaded with the workload, but the average load is between 1/3 and 2/3 of the working load. By selecting a load spectrum of 2 and a maximum number of load cases of 2 million, which gives us a utilization class C, we end up with an element group of 5. Furthermore, we need to select the type of welding, or the notch group, and in our model we keep it more or less simple. Out of the 7 possible classifications, we only use 3 of them. We have the part where there is no welding at all, which is W0, which is the best category. Then we have stresses along a weld, which are defined as notch group K1, and for stresses perpendicular to the weld we use a slightly heavier notch group K2. Now we go back to VMap and SDC Verifier. All calculations are done, so I close the calculation window, and we can now use the standard, and as we see here we can choose the DIN 50018 or the very similar grain code, the FEM 1001. The only difference between the two is that the FEM 1001 for fatigue has 8 classes, while the DIN has only 6 classes. Okay, we open the window of the DIN 50018 and we see that we have to classify the weld type, the element group, and the material type. So for the weld type we select for the full model W0, which means no welding. Then we have to select for all welds, we select the component which is already defined by the weld recognition model, and we say all welds have a classification of K1, and we override that directly by for all stresses perpendicular to the weld into a K2. So we select K2, we select the stress direction perpendicular to the weld. Since we updated all weld direction, the Y direction is perpendicular to the weld, and we apply that to all nodes for each element which is connected to a weld. So the 4 possible corners and either the top and the bottom location of the plate. Also we need to select the component again, so we select for all welds we have a K2, and for the intersecting weld we don't have a stress along the weld, we always have a stress perpendicular to that, so we add an extra factor for all intersection welds, which is always K2. So in this case we first have for the full model K W0. We made an error, so I changed that. Then we have all welds K1 in KY, that is in the Y direction, so in the perpendicular direction, that's overwritten by K2. And for intersection welds, all directions in X and Y are classified as K2. We can plot the result of that. If we look at the perpendicular classification, we can see that there is either a weld, which is a K2, or no weld, which is a W0. And if we look at the X direction stress, then it gets a bit more complicated, because for the stresses along the weld we have a classification of K1. For intersection welds we have a K2 in that case, and for non-welded items we still have W0. Okay, so we're done with the weld classification. We now need to find the element group. As discussed before, we use element group B5 for the full model. Apply, close. Material type, we have for the full model we use standard mild steel, and for all materials which is not mild steel, which is S235, we use S355, which is in the DIN 50018 name FE52 or FE510. So also here material classification is done. We only need to describe also material yield and tensile stress. For the S355, the tensile strength is 520 megapascal and yield stress is 355 megapascal. For mild steel we use 360 megapascal for tensile strength, and for yield stress we use 235. Okay, hereby we're completely done with the standard description, so we click on OK, and what we will see, we can see the classifications we added: weld type, element group and material type, the standard tables used for mild steel and slightly higher strength steel, S355, and two checks are generated, which one of the two is fatigue check, which we can look how that is built up. If you want, you can change every single part of this formula, but for this tutorial we don't want to do that, and we focus only on doing the fatigue calculation. So we are happy with this. Click on OK. We now can open the already created plot. What do we want to see? We want to see the utilization factor. What is the utilization factor? That is the calculated stresses divided by the allowable stress, taking into account the fatigue rule of the grain code. We can see here that there is the standard options for VMAP. Since we used weld recognitions and we have elements which are welds, and we have elements which are no weld, averaging doesn't make much sense, so we unclick that, and we can look how the stress results look. Since SDC Verifier only calculates results when you really need them, by clicking on plot, you can see that the calculation in SDC Verifier starts to run. You can see the individual loads, the underlying individual loads being calculated, results transferred to load sets, and also to the load group, where the maximum and minimum stress for every element and every point of interest is calculated. If we look at our results, we can see, for example, that at locations where we expect to have high fatigue stress, we find them. You can see that this element at the outer edge has some peak stress there. Bottom also shows some results. Since we also directly want to make a report, we immediately take advantage of walking around and saving the detail viewpoints we're looking at. We don't want to show deformation because if you look at a certain position, might be slightly different between one load set and the other. So in general, if you want to look at the detail, you don't want to show the deformed style. Detail 1. Maybe we also want to look at the top. Top view. Top view. Also no deformation. Get location there. And maybe we also want to see something at the bottom. Let's call this detail 2. No deformation. Okay, that's also done. We can make extra plots where we want to see, instead of only a stress variation which depends we make an extra plot where we can see, instead of a varying stress for each point of interest, we want to see only one result. So we use the custom check criteria plot. And what do we want to see? We want to see a utilization factor. We want to have the maximum stress found in the element. We want to check the overall direction, which is a combination, the worst calculation of the stress check or fatigue check in every stress direction. What we also want to do is, for a report, we want to make a component table where we directly can see, for example, for all properties and for all components, we want to see we can see for each stress direction the stress output for every different selection. And here we have the overall check, which is a formula of x, y and a combination, and the overall check, which needs to be below 1. Okay, let's report all our results. We again want to have a front image with a model on it. We already made a model description report, so we skip that now. We use the standard description of all loads and all individual loads results. We want to have a table, displacement table for each individual load, for each load set and for each load group. The plots already created is one displacement plot and one stress plot. That also these are made for all individual loads, all load sets and all load groups. And for the standards, we would like to have for the fatigue, already 2 plots are made. We make an extra one. We want to have the overall utilization factor. We want to do that for all entities, but we also want to look only at all welds where you can peep through from one side to the other. And by selecting all views and selecting both selection, we create now 8 different views. And also here we go to the designer, where we can see in the menu all the fatigue check plots. We can see first the table with for every property and every selection an outcome. Different plots, top view, top view, but now with only the welds selected. Detailed view from the bottom, detail 1. Then after that detail 2. And also here we can walk through all the results for our fatigue calculation. If we also want to include the standard results from all our jobs, we generate the full report. This report will also be available for downloading at our website, so you can see how quickly we can make a full calculation where you get a complete overview over the total calculation, all settings, all classifications, and a complete fatigue calculation. Because 4 minutes is a bit too long for this video, we speed things up and we directly go to the end. And now being 4 minutes further, and the complete report is finished and can be exported to Word. That's the last file. Let's export again everything to Word and everything to PDF. Also that will be made available for download, so you can watch how detailed the reporting is. Let's go to our last sheet. This is the end of our explanation on a fatigue calculation with the use of the weld recognition tool. If you want to have more information, get a trial license, or you want to buy the software, contact us and we will respond to you in 24 hours. Thank you for watching.